Hi, my name's Nikon Vafa, and I'll be presenting the paper Memory Checking Requires Logarithmic Overhead. And this is joint work with Alet Boyle and Alon Komarkodsky. We're going to be in the setting of remote cloud storage today. So your goal is to perform some computation that requires lots of storage, but you don't have enough to run the computation yourself. There are many natural examples like file storage, or maybe you're running some experiment with lots of data or so on. And the common solution is to use a remote cloud server as your storage mechanism. So here's the basic setup. You're a user, you have some data source, and you're interacting with a server that's passive. It's doing nothing besides storage. And let's say you want to write some data to give an address 3, some data prime to some address 8, and let's say you want to read the third address, you should get back data from the server. And you can overwrite data at address 3, for example, and so on. This naturally motivates a few questions of trust. One trust concern is a basic privacy one, that the server may see your data. And thankfully, secret key encryption and cryptography naturally solves this task, or secret sharing if you have multiple non-colluding servers. Another more subtle privacy trust concern is that the server can see where you're accessing. And this actually can turn out to reveal a lot of sensitive information. And the solution to this is oblivious RAM, or ORAM, introduced by Goldreich and Ostrovsky. Another concern is integrity, and this is the one we're going to be focused on in the talk today, where an active malicious server, instead of a passive one, may modify your data. And ideally, we want to make sure that the server is behaving honestly. And as an aside, I can mention that you can imagine combinations of trust concerns like privacy and integrity simultaneously. So what is integrity? What do we really mean by verifying honest server behavior? Like, can we prevent an adversary from modifying the data? Well, on the surface, no, we can't, because say the server could just delete your data, and if you don't have a lot of storage, you can't prevent this. But what we can hope to do is prevent the adversary from undetectably modifying your data. And this is exactly what a memory checker does. To put it another way, a memory checker is a protocol that prevents adversaries from undetectably modifying your cloud data. And this was introduced over 30 years ago by Blum, Evans, Gemmel, Conan, and Naur. So here's the setup as before. We have the user on the server. Now we have some intermediaries, some MC for a memory checker, standing in between these two. So the user can issue a read or write RAM query to the memory checker. The memory checker can then issue a bunch of read or write RAM queries to the server. And then finally, on a read from the user, the memory checker is going to give some response back. And the user can do this many times by issuing many read or write queries to the memory checker. And just to make the language more clear, I'm going to call the queries between the user and the memory checker logical queries. And I'm going to call the queries from the memory checker to the server as physical queries. The basic completeness definition of a memory checker says that if the server is behaving honestly, in other words, it's correctly behaving as a passive storage, then the memory checker is going to give the correct response back to the user, indicated by the screen check mark. The more interesting property of a memory checker is soundness, which says that for any probabilistic polynomial time, or in other words, efficient malicious server, the memory checker is either going to raise some flag and abort, or it'll give the correct response to the user. So in other words, it'll never give an incorrect response to the user. It's either correct to the user, or it indicates some general failure condition. There are two main efficiency metrics that we care about in memory checking. One is local space, which is the amount of space that the memory checker can store locally in a trusted way. And you can imagine private or non-private versions of this. Everything I'm going to say today is going to apply to both settings. For storing n logical entries, if you have local space n, then there's a trivial construction where the memory checker just stores the full RAM itself. So for the rest of the talk, we're going to assume that space is at most n to the 1 minus epsilon for some epsilon bigger than 0. And this little RAM icon within the memory checker is going to be the thing that refers to the local space contents. The second efficiency metric that we really care about is query complexity, or overhead. And this is going to be the number of physical queries, these query hats, made from the memory checker to the server per underlying user logical query. So in other words, it's the number of arrows going from the memory checker to the server here. Let me summarize what's known for memory checking with local space n to the 1 minus epsilon. So in a statistical soundness regime, where you want security even or soundness even against adversaries that are not computationally bounded, there's an n to the epsilon upper bound in terms of query complexity or overhead. And there's in fact a matching lower bound of n to the epsilon, so this is tight. And more generally, there's a tight trade-off where the local space times queries is linear in n. In the computational soundness regime, which is what we're going to be in for the rest of the talk, where the soundness condition only applies against computationally bounded adversaries, there's an upper bound of log n by using a Merkle tree. So here the local space is going to store the root of a Merkle tree, and for every logical query, the physical queries are going to query the path from a leaf to the root in the tree, incurring a log n overhead because it's a binary tree. In fact, Papamonthu and Tomasia showed how to optimize this to a log n over log n overhead construction, which is similar in nature to a Merkle tree. But one can ask, is there a lower bound showing that this is tight? Dwork, Nauer, Rothlu, and Vaikunthanathan showed a restricted lower bound that says that if the memory checker is what's called deterministic and non-adaptive, then the query complexity is at least log n over log n, showing that the construction of Papamonthu and Tomasia is tight. But what is this restriction of being deterministic and non-adaptive? It says that for every logical user query to an index I, the physical query locations are fixed and depend only on this index I. In other words, the sequence of physical locations looked up is the same for a given I, no matter what. And in particular, this means that there's no randomness that's allowed in choosing where you're going to look up the physical query locations, and there's no adaptivity either within a given logical user query or between different logical user queries to the same I. And there's a broad theme in theoretical computer science that both randomness and interaction or adaptivity can help with efficiency. So it's natural to ask, like, is there a general lower bound? Like, what's the right answer? Our main result is that every memory checker must have query complexity at least log n over log n. So this is tight up to constant factors by the construction of Papamonthu and Tomasia. It's unconditional. We don't use any computational assumptions or any crypto. And it handles randomized and adaptive memory checkers, unlike the lower bound of DNRV. So just to complete the picture, we can now put this lower bound in the bottom right corner. One can also consider a generalization where the read and write query complexities differ. Like, let's say you're doing lots of reads, you want the reads to be extra efficient, and you're willing to pay more for the writes. So let Q sub R and Q sub W denote the query complexities of the reads and the writes. We show that if the read query complexity is sublinear in log n over log n, then the write query complexity has to be super polylogarithmic. And in a more extreme setting, if the read query complexity is constant, then the write query complexity has to be polynomial in n. And we can summarize it loosely by this figure here. And in fact, these 3 points are all tight. They're matching constructions given by DNRV, showing that these trade-offs between reads and writes are tight. And previously, there's no lower bound known for any read or write trade-off. One could also ask about the reverse. Is there a memory checker with a write complexity 1 even and read complexity log n over log n? This is still an open question, but we give some partial answer, saying that if the memory checker is deterministic and non-adaptive in the same sense as DNRV, then we get the exact same dependence, but in the flipped sense, like replacing reads and writes. And so we get the exact same figure here, but replacing what the axes mean. And this is, once again, tied up to constant factors, but for the class of deterministic and non-adaptive memory checkers now. And we give some weak evidence in the paper that it's not clear how to extend this to randomized or adaptive memory checkers in the lower bound. Let's give some direct implications of our results. So Wang et al. Introduced a notion of locality of memory checkers, which counts the number of non-contiguous physical query locations per logical query. In other words, it doesn't count. You're allowed to make a bunch of queries that are close to each other or adjacent in physical memory. And this is motivated by systems efficiency concerns. And roughly speaking, they show that the locality has to be at least the query complexity. And so now by plugging in our lower bound, we get a locality lower bound of log n over log n for any memory checker, even those that are randomized and adaptive. Mathialagan introduced the notion of parallel memory checking, where you have many users simultaneously and in parallel accessing a given piece of memory. And here, by plugging in our results, we get a total work overhead of log n over log n, even for randomized and adaptive parallel memory checkers. Also, one can consider the question of compiling an honest but curious ORAM, or a standard ORAM, into a maliciously secure ORAM, one that satisfies privacy and integrity. And by plugging in our results and combining with previous work, we can show that there's no black box compiler from honest but curious to malicious that has overhead less than log n over log n. Okay, let me summarize what's known in terms of the trust concerns that we had at the beginning. So if you want privacy in the ORAM sense, there's an upper bound of log n, which is amazing. And this matches the lower bound of log n, showing that this is tight. If you care about integrity and memory checking, there's a log n over log n construction, and we show that this is tight. And lastly, if you want privacy and integrity together, previous work shows an upper bound of log n, and this matches the ORAM lower bound of log n, which directly applies in this setting. Okay, let me proceed with a technical overview of how we show our lower bound. Let me start with the DNRV approach, which only works for deterministic and non-adaptive memory checkers. They do it by first starting out with a base case, where the query complexity is 1. So, okay, if you have a query complexity 1 memory checker, then they show that the local space has to be at least linear in n. And this is shown by some direct compression or communication argument, and we'll see the flavor of this later, so I won't get into it for now, for the sake of time. And then they show how to reduce a general memory checker into the base case by looking at 2 different subcases, depending on how spread out the physical locations are in the memory checker. And all of these steps really use determinism and non-adaptivity, as we'll see. Okay, so the first subcase is when many physical locations are heavy, or sufficiently heavy. And what do I mean by that? So consider the logical memory and local space on the left, physical memory on the right. By using the fact that we have a deterministic and non-adaptive memory checker, we can consider a bipartite graph between the logical memory and the physical memory. And we can look at where in the physical memory are there a lot of queries coming from. So here we have 2 heavy physical locations, let's say, these top 2 locations in the physical memory. And what the approach here does, it says that if you have these heavy locations, you can move these heavy locations into your local space. When doing this, you can restrict your logical memory of your memory checker into just those that touch these heavy locations. Yeah, so we've got rid of the bottom logical memory cell here. The benefit here is that the query complexity is going to decrease. And this is because everything in logical memory touches those heavy locations, and those heavy locations you now don't have to do a lookup into physical memory, you could just look locally. So your queue is going to decrease. But the cost of this is that your local space is going to increase to include these 2 physical cells, and your logical memory size, your n, is going to decrease from, say, 5 to 4 here. Okay, what about the other case, where there, Rn isn't really a heavy set? So say you have something like this, where it's more balanced. What they show is that you can prune off logical indices so that the remaining physical locations are disjoint. So here we've gotten rid of the bottom 2 logical memory cells. And if you look at the physical memory, the places that it looks up are now totally disjoint. And so if you squint at it, you can interpret it as a memory checker with query complexity 1, where we can combine all of the physical locations that correspond to a given memory cell, logical memory cell, and there's a query equals 1 memory checker. So the benefit is that Q is now 1, and so we can apply our base case. But the cost of this is that the word size is going to increase to incorporate these large physical memory cells. and the logical memory once again decreases here from 5 to 3. Before moving on, I just want to emphasize that like both of these techniques really relied on the fact that the like dependency between the logical memory and physical memory is fixed. If there's any randomness or any adaptivity happening, then this connection goes away. And so our approach is, instead of iteratively reducing the memory checker to some base case, we're going to run a compression argument in one shot. In other words, like a memory checker that's too efficient can be used in a communication style argument to compress random bits of information. And here's the sort of lemma we're going to use. If you want to transmit a uniformly random subset S of size k from Alice to Bob, this is going to require log of n choose k bits, even if Alice and Bob are allowed to share some random string that's independent of S. Okay, let me give a first attempt. So we have Alice on the left, Bob on the right. Alice knows the subset and wants to communicate it to Bob. Alice and Bob are going to publicly initialize some memory checker, say writing zeros everywhere. This is going to result in some public physical memory db0 and some local state st0 after doing this initialization. Okay, now Alice gets to look at her set S, and she can write 1 to every I in S into the memory checker. So just write 1 as the data. And this is going to spawn some changes into db0. And the number of changes is going to be at most k times q, because there are at most k writes happening, and the query complexity is q. So for each of these k writes, it can change at most q locations. And of course, things have changed now. db0 becomes, let's say db1 is the updated database, and it'll have some updated local state. Let's call it st1. Alice is then going to send over just this updated local state to Bob. And then Bob is going to run the following recovery procedure. Bob is going to try reading, for every I in n, it's going to try reading I into the memory checker. But the issue is that it doesn't have a db1 like Alice has at the end. Instead, it only has a db0, which Alice and Bob shared at the beginning. But nonetheless, Bob is just going to run this and see what happens. If the memory checker spits out r sub I that's 0 or 1, then we're totally in business. Because the soundness property of the memory checker says that if you have an output from the memory checker, it's 1 if and only if, here in this case, if I is an S. Yeah, so the soundness memory of the memory checker exactly indicates whether I is an S. So Bob can figure out this bit of S. But the issue is, of course, that the memory checker could abort, could raise a failure symbol, because db0 and db1 differ. And so what do we do in this case? It's not so clear. What we can do is we can hope that for many logical indices I, when Bob calls read of I, it'll avoid all of these modified gray cells, as these gray cells are exactly the difference between db0 and db1. If this is true, then we can invoke completeness and recover most of this set S, and then we'd be in business. The issue, though, is that what if, like, let's say even all logical queries look up physical locations that are going to overlap? For example, in a Merkle tree, this happens. Every logical query is going to induce physical queries that all touch the root of a Merkle tree. And so they're all going to touch the gray cell, and so there's no hope. But of course, a natural idea we've seen is to partition this database into heavy and light locations, similarly to how DNRV does. We'll call them H and L. And now Alice can send the updated heavy contents to Bob, and hopefully there shouldn't be too many. And what we can do is we can hope that when Bob calls read of I in the recovery procedure, this will avoid not all of the gray cells, but just the light gray cells, because Bob has the updated heavy contents, so it doesn't have to worry about those. Okay, so one can show, unfortunately, that a two-way partition into heavy and light, as I've described it, is not good enough. And I don't have any good intuition, unfortunately, to explain it in a short amount of time, but essentially some vague ideas that you need some gap between the heavy and the light set in order to get some meaningful communication lower bound. However, what does work, miraculously, is a three-way partition. So we're going to have a heavy set, a medium set now, and a light set. So the heavy set is as before. A medium set is going to have some total guarantee that the probability of the full medium set is low. And then we have a light set that has some pointwise guarantee of low mass, meaning that every individual element in the light set has a low probability, as opposed to the whole light set having in total low probability. And what we show is that 99% of we can set parameters so that 99% of reads avoid both the medium and the light elements that touch these gray cells. Okay, so here's our first attempt that we had before. Now what's going to happen is that in our final attempt, Alice is going to run this heavy, medium, light decomposition. And then Alice is additionally going to send over a description of the heavy set and the database on the heavy set, the updated database on the heavy set. So now Bob has some hybrid database between DB0 and DB1. So it's DB1 on the heavy set and then DB0 on the light and medium set. And by our previous parameter setting, Bob can recover a lot of the set S, and they'll win. Taking a little bit of a step back, our inspiration for this techniques comes from relaxed locally decodable codes. So what's a locally decodable code, an LDC? It's an error-correcting code with the additional property that recovering a bit of the message takes few queries into the code word. And one can relax this notion into a relaxed LDC that allows the recovery procedure to abort if it detects some error in the code word. And so our three-way partition lemma instead of a two-way partition lemma is inspired by lower bound techniques applied to these RLDCs. And specifically, a lemma that looks quite similar to ours appeared previously in a work of Goldreich. But it's used in a little bit of a different way, in a different manner, but the technique is similar. Okay, let me summarize. Memory checkers remove the need for trusting integrity when using remote cloud storage, and we prove tight unconditional lower bounds for memory checkers, showing that Merkle-style constructions are optimal. And previously this was known only for the special case of deterministic and non-adaptive memory checkers. For an open question, one can ask about a read or write trade-off, and specifically, is there a memory checker with write query complexity 1 and read query complexity log n over log n. So this is open, but we show that the answer is no if you restrict to deterministic and non-adaptive memory checkers, but we don't know how to generalize this. All right, thank you so much for listening.